Okay, so this one is about Young's double slit. So with this, we're looking at the interference of light as it goes through a double slit pattern. So we can see that we've got the two diffraction patterns happening here. Okay, so in this case, I've actually used the light already being coming from a single slit, going then through a double slit. So this could be like the opening of your laser pen. With this, we know that when we've got the two lights, these would be a coherent light source, so light of the same type, of the same frequency, with a constant phase difference. We're going to get these areas of maxima and minima. So areas where the wave is in phase, the areas where the wave are out of phase. Okay, so again, if I'm looking at this here and I wanted to see where they're in phase, I can follow it along. Again, from the middle, all right, we get to then the central area here, which we would call a maxima. Okay, so this would be our central maxima, and I'm just going to use the maxima's numbers as calling the central 0. Again, I can follow up through the second, for the next one and go along, and I get to n is equal to 1. I could go up further again, and I could get to n is equal to 2. Okay, I also then get these areas of minima. Okay, so in each case there where maybe the waves are out of phase, so they're interfering destructively, we get this area, and this is called our fringe pattern. Okay, so I'm just going to turn it around, so we get an area going along of bright fringes, bright fringes, and dark fringes. Okay, so just remember this would be a maxima, and this would be a minima. Okay. So in each case, we've got the light going through. So if you need a little bit more help, have a little look at the constructive and destructive interference video and the path difference one, and that'll give you a little bit of help. Okay, so when we're looking at Young's double slit, what we're going to look at is how this interference pattern is formed, about the characteristics of it. So S here, okay, is actually called the fringe spacing. Okay, so the spaces between these different fringes, all right, or sometimes they call it the fringe width, all right. So that in here is given by the letter S. Okay, S is equal to the lambda, so that's the wave, the type of wave that's being produced. Remember, it's a coherent wave, so that's the lambda of the wave that's being emitted in. D is the distance from the screen. Okay, so from the slits to the screen here. So this would be our D in this case. And then little d here represents the distance between the double slit. Okay, so in this case, that would be giving us this equation. So often this question may be just me asking you to find out, calculating the fringe distance, so the fringe spacing, or the fringe distances or separation of the fringes. It could ask you to calculate the distance between the slits, or maybe the wavelength of the light given, depending on what they've given you. They sometimes also like this question to be a little bit more theoretical, and they could change this in different ways. Okay, so they might ask you what happens, for example, to the thickness of the fringes. Okay, so if I was looking to make the fringes what would affect them, okay, I could maybe change the light, I could change the distance from the screen, or I could change the fringe spacing. So in this case, if we're changing the distance of the screen, so if I made the distance from the screen bigger, okay, so I made this distance larger, I'm also going to increase the the separation of the slits. Okay, I could also maybe increase the spacing between the double slits. Okay, if I do that, I'm also going to decrease the fringe spacing. Okay, the other one might be to do with what type of light am I using. Okay, so if I increase the wavelengths, I'm going to higher wavelengths. All right, again, if I increase the higher wavelengths, then I'm also going to be increasing the width of the slit. So you can just about see that on my page there. They sometimes don't rephrase this as waves, as waves, they might wavelength. They might also refer to this as frequency. So if I increase the frequency of the wave, increasing the frequency decreases the wavelength, then the slits would go down. They also sometimes put this in as a multiple choice question, where they ask you about the types of light. Okay, so if we're looking at visible light, we might be using colour. We could use the electromagnetic spectrum. So we could have, we use the electromagnetic spectrum. Okay, we know that as we're going from this, we've got our longest wavelength going to our shortest wavelength. Okay, if I'm looking at the visible, and I've got red, viv, again with this, we've got them going shorter. So again, a red wave, okay, would give a greater fringe spacing than violet light, which would give a smaller fringe spacing, because violet has less wavelength in there. So sometimes they like to put these as a wordy question, sometimes they like to put them in as a calculation question. But simply with this, we're just using the application that we've learned about interference to explain why we get this series of maxima and minima. One of the more challenging ones that they sometimes ask about with this, and I'm just going to turn, actually I'm not going to turn the page, is they sometimes ask about the intensity of the light. Okay, so looking at these, which of these fringes would you expect to have the brightest fringe? Most people kind of intuitively always say, well, the middle one will always be the brightest, but that's not going to get you the marks in an exam, okay? So it is going to be the brightest one in the centre, but we have to think about what's happening with this. So in this case, we've got both of these waves, okay, coming to this point, all right? So we've got our difference between those waves there, or how far they have travelled. If we want to go up to the next one, we're actually having to change the waves to travel even further, okay? And if I want to go up to the third one, okay, so my N2 up here, all right, I'm having to go an even further distance. So in all of these, we can see that light is travelling further to get to that last one there. Now, if we remember about intensity and we remember about with its relationship with distance, we know that intensity is inversely proportional to the distance squared. So it's got that inverse square law. Okay, so as we go further away from the central maxima, the intensity decreases because our distance is increasing. And I think that's about it in terms of Young's double slit and types of questions they could ask you. If you have any other questions or you want me to do a little bit more detail, please let me know.